Greetings, friends of astrobiology. Welcome to a brand new episode of Ask An Astrobiologist, a show where we celebrate science and celebrate scientists. My name is Sanjoy, and this program is made possible by contributions from the NASA Astrobiology program and the nonprofit Blue Marble Space. Last month, my fiercely bearded co-host, Dr. Graham Lau, known as the Cosmobiologist, interviewed Dr. Jill Charter, and we talked about the value and the necessity of exploring for life beyond our home planet. This month, we have a really exciting guest, and we will continue this conversation, Dr. Sarah Rugheimer. She's a fellow at the University of Oxford, outstanding astronomer, riveting dancer, fearless mountaineer, and we're going to be talking about all these topics in a little bit. But first, it's time for your monthly background quiz. So last month, Mike, if you could put the picture up, we had this beautiful picture behind Dr. Graham Lau, and several of you got it right. It is, of course, a Badwater Basin in the state of California in the United States. It is a basin at minus 86 meters below sea level, so it is the lowest point in North America. And just about 100 miles from there, you can see Mount Whitney, which is the tallest mountain in the lower 48 at 4,420 meters. So quite a big distinction in elevation there. So for those of you who got it right, congratulations. The third place winner will get the NASA stickers. Congratulations. The second place winner will get the stickers and the graphic novels. And the first place winner wins it all with the stickers, the graphic novels, and the SIGNET Pine Class. Congratulations. All right, it's my great privilege to introduce to you Dr. Sarah Rugheimer. So you're an astronomer, and I was wondering if this interest in science that later blossomed into a career in astronomy and astrobiology, is that something you had in mind early on as a kid?
Short answer, no. The long answer is there was a moment in my childhood where I liked astronomy, but quite frankly, I swore to my dad when I was in high school, I said, I'm never going to take a physics class as long as I live. And that's because he's a physics professor and my brother is also a physics professor, and basically all of my brothers and sisters have a degree in physics of some sort. And so I said, I'm going to do something different, And so I decided to take accounting instead, and it was really boring. And the only class that would let me switch into that late in the term was physics. So I ended up taking physics in high school, despite my declaration that I wouldn't. And I enjoyed it, but I was never going to major in it. Never at all. And so when I got to college, I was thinking about doing other things, and I got through my first year and I was thinking, what did I enjoy? And I'm like, well, I liked physics. And so then I did a major in physics, realizing that it was stupid not to major in it just because my family has a lot of physicists in it. But I swore I would never do astronomy. So then, all through undergrad, I said, I'm never going to do astronomy because it's squiggly lines all day long. I mean, that was the impression I had of astronomy. I went on a summer undergrad research project and I watched my fellow summer undergrad students doing astronomy projects, and they were literally just going through 700 quasar spectra a day, going yes, no, kind of double checking the pipeline. It looked to me to be the most single boring job on the planet. And so I said, I will never go into astronomy. I never took a single astronomy class in undergrad, not at all. I didn't go to any astronomy talks or anything. And I even had a professor in undergrad try to get me to do an astronomy project with him. And I refused many times. And he pushed me so hard. I was like, I just don't want to look at squiggly lines all day, is what I said to him. And now what do? Is I generate spectra and look at squiggly lines all day. And, it's what the lines mean. But when I was in my, youth, I was not so smart and did not realize that. So it took a while of me saying never many times before I got here.
So tell us a little bit what a spectroscopist does. What is a spectra? Why is that important in astronomy?
Yeah, so again, it's these squiggly lines, it's what they mean. So lines absorb at very specific wavelengths of light. Molecules absorb at very specific wavelengths of light. And so by looking at that, we can actually see what's out in the universe, whether it's in a star or in interstellar dust or on an exoplanet. And so it's amazing to me now, sitting from this position of being an astronomer, it's quite amazing how much we can do by just passively collecting light on Earth, how much we can tell about the universe from its origin all the way to, planets and stars and other planets that are orbiting other stars. And so my interest in astronomy is particularly, could we tell if there's life in an exoplanet from Earth? How could we tell? It's going to be difficult because we can't send, a microscope to the surface and look for little things, squiggling around in the ocean. So we have to do this all by just looking at what's imprinted on in the atmosphere, and how you do that is through spectroscopy and what wavelengths get absorbed by different molecules.
So that's because biology on a planetary surface would operate in such a way to completely change the air, what the air is made of. I mean, if we think about the Earth today, the air that we breathe would be nothing like it is if biology had not evolved on the planet in the first place. So what about the air on a planet that's alive is different, and how can you detect that?
Right. Well, so as you said, I mean, in some ways, Earth has been many planets, through its history. Yes. We often think of Earth as just being a single planet, but it's gone through such a dramatic change from its formation to today that if you were to take a snapshot at any given point, it would look very different. And so, sure, we breathe air, and it has a heavy imprint of life on the atmosphere. And that's the only hope we really have of seeing life around another star. If the life is really subsurface and not really interacting a lot with the atmosphere, we're just not going to be able to see it. Case in point, Mars might have life living in the subsurface, and we can't tell, and we're right next door. So for an exoplanet, we're trying to see, is this planet have a whole global biosphere, an atmosphere where that life is interacting with the atmosphere, and then it's leaving fingerprints of different molecules in the atmosphere, things like oxygen, methane, nitrous oxide, methyl chloride, all sorts of different molecules that we might try to look for, to try to tease out, could that happen from just geology and physics and chemistry, or does it really need something like life that's driving it? And so that's the ultimate goal.
So are you looking for specific compounds or more like mixtures of compounds?
I would say ultimately we need to see more than one molecule. So one single biosignature gas will not be enough. And this is because even if you were to detect oxygen, we know now of many ways to get oxygen without life. And so you have to look for other ways to distinguish between those false positives, other molecules in the atmosphere, and look for other combinations of gases. So one of the most commonly cited and strongest combinations would be something like oxygen or ozone with methane, because both of those gases together would be difficult to maintain at concentrations unless produced by life. And so that's a target that is often talked about.
Well, that's a big step from going to college and not wanting to take an astronomy class to being able to detect compounds in planetary atmospheres that are not the Earth. Tell us about that journey you took to end up at this stage of your career.
Yeah, so maybe I'm being too honest, but I will say I went to a undergrad REU program in Hawaii for astronomy, mainly because it was Hawaii, not because of the astronomy. And I really, that also didn't convince me after that summer. I remember my advisor asking me if I thought I might want to do grad school in astronomy, and I was like, no, not really, And I still was just really dead set against astronomy at that point, and I was going to do an MD PhD. That was what I was leaning towards, and more of the work that I had done in undergrad was more medical physics. And then what happened is, because of that REU in Hawaii, I went to a conference, a AAS conference, the next summer. So this is after I graduated, and I took a year off between undergrad and starting grad school. And so in that summer, that first summer after I graduated, I presented my summer research findings at this conference, and I sat in on a session on astrobiology and detecting life on another planet. And I just was like, what? We can do this? This is a question that could be answered in my scientific lifetime? No one told me, And I was so excited that. And that, honestly, I never looked back from that point. And I still think it's just by far the most interesting area of science. And then I came across a book and a teaching company series by Bob Hazen called Well, the book is called Genesis, The Scientific Quest for Life's Origins. It's this book. I highly recommend it. It goes through a lot of prebiotic chemistry. And I just got really excited about not only how to detect life on an exoplanet, but, trying to tease out the origins of life on Earth. And when I realized that for the first time in the history of humanity, and we've had this question of, are we alone? What's our place in the universe? We can begin to answer this from a scientific standpoint. I just was hooked. And so then I only applied to grad school in astronomy. And when I showed up, I felt really out of place because I hadn't taken any astronomy undergraduate classes, and astronomers use all sorts of weird units that are not SI, like ergs and AU, and I felt completely lost by the jargon for the first 6 months and almost dropped out, quite frankly, from that feeling of just being like, oh my God, what's happening? But I'm here today, so.
I empathize. I started grad school in geology, never taken a geology class, so the first year was tough, but we survived. So it's actually the astrobiological aspect of astronomy that got you excited into the field.
100%, yeah. No, I mean, I like the rest of astronomy now, but really it's the astrobiology I'm here for. Yeah.
So you went to graduate school at Harvard, if I'm not mistaken. Tell us how that experience was like, particularly because you didn't feel exactly whether or not you belonged there. So I'm sure you relied on some mentors and friends. Like, how did you? I mean, grad school is not easy. How did you do it?
Yeah, absolutely. It was really hard. Mainly, I fell out of place for a couple reasons. One is I hadn't had the astronomy background. Every other person in my class knew that they wanted to be an astronomer for a lot longer and kind of already had the background. As well as they had all gone to fancy undergrads by and large. And so I had gone to a community college first in Montana and then to a school in Calgary in Canada for my undergrad. And so I just really felt quite out of place, and I remember about 6 times that first 6 months calling my dad and just saying, I just want to drop out. I don't feel like I'm smart enough to be here. I don't feel I belong. And my dad was like, just, give it some time. You'll be okay, and those feelings faded, but that feeling of the imposter syndrome, which really hit me strongest in grad school, and most people it impacts them the first time really in a big way in grad school, was very present. And part of that narrative was having not come from, MIT, Princeton, all these other places. And then combined with the fact that I didn't know anything about astronomy, so I was, lost. I remember in my first day of my first class, my supervisor, Dimitar Sasalov, was teaching and said, oh, well, you guys already know hydrostatic equilibrium, so we're just going to skip that. And that was never covered in any of my physics classes. And I was just like, oh my God, we're just skipping all of this stuff and I don't even know where we are. So, and then he said units and things that I'd never heard and all these acronyms. I remember not knowing that Hubble was HST, and so people were talking HST, and I'm like, what? And I'm like, oh, Hubble, oh, okay, I got it, But it was just really like all this lingo that I didn't know, and I felt really quite out of place for the first year or so.
So I'm sure you had some good friends there. I know Sarah Ballard, somebody you're close to, and you guys did a blog together. Probably still have that blog going.
We sure do. So
tell us about that.
To answer the second part of the question, how did I survive? So it was really the cohort of people I came in with. I just really had a great experience of the other students in my program, and we were all very supportive of each other. And Sarah Ballard, in particular, when I would open up about how I just fell out of place, I don't feel I'm smart enough, I'm not going to do well, she would just say, you have the imposter syndrome, you have the imposter syndrome, you have the imposter syndrome. And I literally thought she was just making up an entire psychological syndrome herself that she called the imposter syndrome. I didn't think it was a real deal. And so she said this to me, I don't know, 14 times or something. And then I was texting a friend from undergrad, and I was like, yeah, my friend calls it the imposter syndrome. And he said, oh, that's a real deal with a Wikipedia page and everything, right? And I said, what? And I went to the Wikipedia page and I found the woman who termed imposter syndrome. And I started writing her an email, and I'm like, I get how you observe this in people. However, I think that I am actually, and then I just realized she wouldn't believe me. Like about at that point in my email, of me trying to tell her why I was the one true imposter and everyone else was fake imposters, I realized that she would laugh at that. So then I never sent that email to Valerie Young. But that was kind of how I first heard about the imposter syndrome. It was through really the strength of the other graduate students and support that kept me going. And then Sarah Ballard and I launched a podcast that we run called Self-Care with Doctors, plural Sarah, because we're both named Sarah. And so we talk about all sorts of things to do with maintaining mental health, physical health in grad school, in postdoc years, for junior faculty applications. We talk about conferences. We talk about surviving grad school. We talk about a lot about the imposter syndrome. We talk about cognitive distortions, exercising, all sorts of things, in our podcast. And yes, we are indeed still going 3 years strong. So check it out on iTunes or SoundCloud.
Remind us the name again.
It's Self-Care with Doctors Sarah. And like I said, you can find it on iTunes or SoundCloud. And yeah, have a listen. Send us any. We love getting questions that people have or feedback or things that they want us to talk about as well. So we there's a email that we always give at the end, and you can tweet at us and all that stuff.
So beyond science, you're pursuing a fair breadth of interests. You're a tango dancer, you're a mountaineer. How do you have time to do all this and science?
I do the other things not all at once, so they come in phases. So for example, like I'm not climbing mountains every day. I climb mountains like once every year and a half. I'll take, maybe 2 weeks to go and do that. And then I've climbed some really tall ones, that are like Aconcagua in South America. But that's like a whole trip that I just reserve and train for at home. But it's not really a lot of time because they happen so infrequently. Dancing, again, I do a lot of ballroom dance, Argentine tango. I competed in Irish dance for a long time, but those have come at different phases. And so I do them in my evenings or weekends to relax and whatnot. But I don't do everything all the time, is what it boils down to.
Seems like it's an important aspect of keeping a solid mental health, is to be able to distract oneself from science, right?
Or have other interests. I mean, I do find when someone says, "Oh, I only do science," I'm like, "Really?" like, all right, we're gonna have a short conversation then, because there's so many other things that are interesting. I do think you need to take that mental break, and then it helps your science because you come back and you are more refreshed and you can think about things again and whatnot. So I try to maintain those, but again, they come and go depending on how busy things are, and I certainly haven't done all of them all the time.
Cool. So in addition to listening to your podcast, what would be like your one piece of advice for some of our listeners and viewers who might be feeling imposter syndrome in class, not even maybe at university, maybe even earlier than that?
Yeah. So I actually have two pieces of advice, and I gave both of those pieces of advice in a commencement address at the community college I went to. So you guys can also see that YouTube video. If you search my name and commencement address, it comes right up. And it's about halfway through the video that my commencement address starts. But basically in that, I always give roughly two pieces of advice. One is don't say no to yourself. So don't self-select out of opportunities. I almost didn't apply to Harvard because I didn't think there was a chance I could get in to Harvard. And I remember sitting at the screen on the application submit button for like 5 minutes because it was a $90 application fee, and I remember thinking I could go to dinner 3 times for $90, like nice dinner, and that was, I just was like, why should I spend this on a school I have zero chance of getting into? And I almost didn't click submit, and that happens so many times. Like I almost don't apply for a fellowship or whatever because I'm like, well, I'm not going to get it anyway, so why bother applying? And in the end, I have to apply to maybe 10 times as many things as you get in academia. That's very common, with fellowships and faculty. You just have to apply a lot. So my advice there is just don't say no to yourself. Let someone else say no to you. Someone else can tell you no, but you don't be the filter that stops you from applying, because the imposter syndrome can really do that. And my second piece of advice is that you really, self-care comes first. You can't be a good scientist if you're not taking care of your mental and physical health. And so And this is something I learned strongly in mountaineering as well. Like, you have to take care of your body first. So that means, sleep comes first, exercise comes first, eating well comes first. And often, social connection, maintaining good social connection comes first. And these things are often the things that go by the wayside when we're most stressed, but those are the things that are also the best buffers against stress and can help you function at your peak level. There's a lot of research on this, and so I go into a bit more detail about it, but in the commencement address. But those are my two pieces of advice: is you got to taking care of yourself is a prerequisite to success, and don't say no to yourself. Let someone else say no. Yeah.
Wise words. Thank you. I was actually going to ask you about the overlap between starting and finishing a scientific project and starting and ending a climb of a mountain, but you've addressed that already a little bit.
Yeah.
So I'd like to dive in a little bit on the science. A few more minutes before I have to share you with our audience in terms of the Q&A. It's regarding, again, these atmospheres of exoplanets. Are we at a stage now that we can actually measure the composition of air on other worlds?
Not for planets like Earth. We can do it for planets that are a bit bigger, a little bit closer, so a bit warmer. So we have some measurements of GJ1214b as atmosphere, but these planets are, maybe 500 Kelvin, so that's a couple hundred degrees warmer than our planet. So they're not like Earth yet. So we're starting to be able to do this for bigger, closer, and warmer planets. Really, with James Webb's Space Telescope launching in 2021, that'll be the first pass at being able to do this for Earth-like planets. And even with James Webb, we're only going to be able to characterize the atmospheres of a handful of planets, not that many. And so we're still not going to be able to have the statistical sample of planets that we ultimately would like, which is why I'm also interested in these future missions like LUVOIR and some HabEx and some of the other ones that are being proposed as that next stage where we can then start to detect hundreds of planets. Atmospheres that are like Earth. So we're just getting there. We're close, but we're not there right yet.
There's the sequence, James Webb Space Telescope, LUVOIR, fingers crossed, and then HabEx? And what's the difference between those?
Yeah, there's a bit of debate. So LUVOIR and HabEx are both proposals for that next telescope after James Webb. So James Webb is going to launch. Let's hope, fingers crossed. It's had a rocky year, but I think the launch date's some March 2021, if I remember, and that will be really very exciting. And I think we'll get a lot of exoplanet science out of it. We'll be able to detect a lot of atmospheres, but they might not be Earth-like planet atmospheres. And then so really, but we will be able to do a handful of Earth-like planet atmospheres, and we'll certainly prioritize some targets, maybe like the TRAPPIST system planets, which have been in the news a lot. And we'll hopefully get some information about those atmospheres, but it'll be really follow-up missions that will be able to detect lots of planets in any number that's more statistically relevant.
I'm going to ask you one last question before I open it up to the audience, and to my colleagues who are working in the ether, please channel the questions to my screen so I can see them. Do you think you'll have a chance in your career to contribute and actually detect life on other worlds?
I hope so. I mean, that's why I'm here. I think at the, it's kind of like anything. They show you that graph of how confident you are, and it varies in time. And it's like you go from being, oh yeah, I can totally do this, to, oh, it's never going to happen, to like, oh, maybe, And I feel like I'm in the oh, maybe part. It's going to be hard. I think it's going to be really hard to know, and we're probably never going to know with 100% certainty. We're going to just try to get a statistical idea and try to tick off all the boxes that we can think of that we know that could have produced those signatures without life, but without absence of going to the planet or without getting some sort of SETI intelligent, like, hello, here we are signal, it's going to be really difficult to tell. And so I'm really excited about it. I think it's absolutely 100% worth dedicating all of my career to. and I really hope that I get to be part of that in my lifetime. I think it'll be, a little, the most optimistic is 10 years that we find something pretty good. I think I'd put more money on the sort of 25 to 40 year time frame. And if it's on the earlier side of that time frame, then I'll still probably be kicking around. If it's like 40 years from now, I don't, I'll still be alive, but I don't know if I'll still be doing science. We'll see.
Oh, rubbish. I'm positive that you will. The enthusiasm is like oozing out of the screen right now. You'll be doing science in 40 years. All right, it is time for the questions, one of my favorite part of the show. The first question, Sarah, is from our user Sleeping in Ria, which comes from Reddit. And the person asks, what do you think is a chance we could find multicellular life on another planet in our solar system?
In our solar system. Interesting. What are the chances? Well, I have zero idea as far as like a number. I do think going to Europa is very interesting because Europa has liquid water that's been stable on the surface, under the subsurface of ice, but interacting with rock and mineral gradients and hydrothermal vent type environments. And so it's been a habitable environment for, 4 billion years. It's very difficult to get to because it's under this huge, 10 to 100 kilometer thick ice layer. How do we figure out if anything's under that ice and get that data back? But I think Europa is an absolutely amazing place to look. And on Mars, I would assume probably the life is going to be more unicellular and subsurface. We've been, roaming around on the Martian surface and even, recently with the death of our dear rover friend on Mars, but there's no kangaroos bouncing around on Mars, so life is probably microbial and subsurface if it still exists today. So for multicellular life, I probably would go for Europa as the most habitable place to look.
I think that would be my bet as well. Next question is by Marianne Denton on Twitter, and she asks as you know, Earth atmosphere has changed a lot by biology as a result of the great oxidation of it. So she asks, thinking about how cyanobacteria facilitated the GOE by producing O2 and causing the extinction of many anaerobic microbes, what would the atmosphere of a planet be if a GOE situation never happens?
Right. So perhaps you just have a lot of methane. And then the question is, can you tease out, say, methane versus just methane produced from volcanism? So methanogenesis is a pretty easy, relatively easy metabolism. It seems to have risen very quickly. Ultimately, life tends to use the same redox energy gradients that also geology tends to use. And because life uses those same redox gradients, those are also false positives because geology can use them. So methane is a good example of this. So on the other hand, Earth life produces, 30 times the amount of methane that the planet just would otherwise produce. So there's some thought to maybe if we were to detect enough methane and know more about the UV environment of the star and other indicators in the planet, that we might be able to say maybe that planet has methanogenesis going on it. But it is more difficult because that's a pathway that's also used by geology.
Cool. Along similar signs of the question, the next is from Julia de Marinis, who's asking from Seganet. And she asks, what are the best gas combinations to look for other than methane and oxygen?
Right. Well, that's difficult. So best gas combinations. There are some that have been proposed, and I'm blanking on them now. I'd have to send you an email, Julia. But I think there are some interesting single molecules that might be good, strong biosignatures, like methyl chloride. N2O has been put forward as a good biosignature. However, we're also finding ways of producing N2O from abiotically. Methyl chloride, some of these other more niche molecules, dimethyl sulfide, they're produced in really small quantities. So, and often only by a single or a few microbes that produce them. And so what is the chance that another planet with life would produce those same molecules, because they're often very niche molecules, is difficult to say. And would they imprint the atmosphere? Would they be a big enough constituent of the atmosphere for us to look for them? But I think that's absolutely worth checking out, because those molecules are more uniquely identified with life. So they'd be a really strong biosignature, but they might be harder to detect. Sarah Seeger has some papers on this where she's looking at like all of the possible molecules that life could produce, trying to disentangle which of them have geological false positives or photochemical false positives, which of them are produced by life, which of them have spectra, and all that stuff. And it's something like 16,000 possible molecules that life might produce on an exoplanet, and we have spectra for 0.04% of those molecules. So there's a lot of work to do to even be able to detect molecules that are on exoplanets, because we really only have detailed spectra for not that many molecules, kind of the big ones that we think of: CO2, water. We have a lot of ozone, oxygen, methane. We have a lot of lines, but to get lines for some of these more niche gases, we need to do a lot of theoretical or laboratory work to get even those spectra to be able to detect them in an exoplanet.
It's worth mentioning that it is an extremely active area of research. These lineless
are really important, and we need to fund that. And this is something that I think we don't appreciate, because we all use lineless, and but it's not sexy to fund lineless, because it's like this basic science, and this is something I think we need to change as just kind of a society where we fund more of this basic research, which will have a lot of implications for the future. But it's not like you see these proposals and it's like, do you choose the one that's like, I'm going to detect, X number of planets, or I need to make some lineless. And often that science gets not funded as much as it should. And we all rely on that data. So that is becoming more echoed in our community. And we're recognizing how even for, Jupiter type planets, like just having better methane lines really changes the observations. And so we're starting to get that message and have more resources, but we do need a lot more of that.
Indeed, I agree with that. Next question is by Tom Caruso from Facebook, and he first thanks you, Sarah, for the time and all the efforts you have done for women in STEM in particular. Okay. And his question is about remote ice-covered ocean worlds orbiting hot gas giants, brown dwarf temperatures.
Yeah.
And he's asking about, is it possible to establish rough atmospheric parameters connected perhaps to the internal geology in an attempt to work with like instrument design, or how can you tune instruments to detect stuff that's interesting in those ice-covered ocean worlds?
Right. So ice-covered ocean worlds have two main problems. So ocean worlds in general, even if they're not covered with ice, have one problem which is often ignored by astronomers, which is concentration mechanisms. How do the molecules come together in concentrations that can create life? That's something that is probably difficult. But when you add also ice on top of it, you're kind of shielding a lot of that from the atmosphere. So the only way we're going to be able to detect something as an exoplanet is if there's enough gas exchange between the atmosphere and the planet, and life on the planet producing a lot of molecule and gas composition in the atmosphere. So for something, again, I would go to our own solar system. Europa is practically our next door neighbor compared to anything else, and we can't tell from here if Europa has life on it. We're going to have to drill through, this ice layer to detect it. And we have orbiters flying around Europa, and we still can't tell. So if there's life on Europa. So I really do think that these ice-covered ocean worlds as an exoplanet are probably not going to be targets that we're going to be able to go for.
Thanks for that. The next question, and we have a lot of them. This is awesome. Thank you all for all these incredible questions. The next question is from Alperen Kaya, who's our third place winner for this month's photo contest. She asks, how do we decide that a molecule is actually a biosignature?
Yeah, so there's so one is it has to be produced by life, like that's clear. But then we also want something that doesn't have a lot of geochemical false positives. And or if they are geochemical false positives, we want to know what other gases can we use to discriminate whether this is from life or not from life. And so, as I mentioned from Sarah Seeger's work, life produces literally tens of thousands of molecules, and so there's a couple of questions then when you see all of the molecules that life can produce. Well, could it produce them in quantities that would leave a spectral imprint on the atmosphere? For most of them, the answer is no. There's just not, even if you had the entire planet covered with this microbe, there wouldn't be enough of that gas in the atmosphere to leave a spectral fingerprint. So you want to see, is it stable in the atmosphere? Is the molecule stable? Is it going to be in the atmosphere for a long time? Does it have other false positives? And could we disentangle those false positives if it does? So biosignatures are not necessarily 100% proofs of life, but they have to be signs of life that we're hopefully then through other gas combinations in the atmosphere have a more clear indication that yes, that is from life. On Earth, the classic example would be like oxygen and methane, as I already mentioned, N2O, dimethyl chloride, or methyl chloride and dimethyl sulfide. These gases all are produced, they have spectral fingerprints, and we can tell that it's not geology. So that's kind of the idea.
Cool. The next one is from Elizabeth Hutton on Twitter, and she's wondering what are some of the most pressing problems in biosignature detection. I think you've addressed a little bit of them, and or early Earth modeling, because early Earth is an exoplanet essentially.
Right. Yeah. There's a number of I think exciting avenues of research. I would say probably the most pressing problem is lineless right now. To be honest, I think it's a really important one. I think also getting a better understanding of time dependence and flaring and activity of stars, which is more my area, I think is important. So that might seem self-serving, but I do think it's an avenue of research that's important. I think, I would say probably those, as well as just better understanding of false positive mechanisms and so how bad can you get? Like right now, most of the false positive mechanisms have been for single gases, but could you have a combination of gases produced in a false positive way? What's the worst case scenario you can envision that a planet is producing something that looks like life, but it's actually abiotic? So kind of teasing out more of that parameter space to see, just to have a better handle on when we start launching these telescopes that can do this, we're not going to be confused or fool ourselves by what we're seeing. And then, of course, I think, just getting more of a handle on what other types of gases life could produce. I think there's kind of two main questions in biosignatures. There's the technological hurdle of just detecting these. That's like one major hurdle. Can you detect oxygen, whether it's from life or not, in an exoplanet atmosphere? That's one huge hurdle. And then the second hurdle is, can you tell if that is from life or not? And those are kind of separate questions in some way. And so I think a lot of the development right now is on the technological hurdle, and a lot of the theoretical modeling from early Earth atmospheres as well is trying to get a handle on the interpretation model simultaneously, so that when we get to the ability of detecting these, we'll understand it better. Yeah.
Cool, makes sense. The next question I quite like from Stanley Suryadinata on Facebook, and they ask is there any research you would like to do if you had unlimited funding and unlimited time?
I mean, if I had unlimited funding, I would just go and fly something like TPF now, or like LUVOIR or, HAVEX or Darwin or any of these missions. I would just take that, $12 billion. Yes, thank you. Here, let's go build this telescope. If I could make $12 billion quickly and in a moral way that's responsible, that's what I would do. Try to get this so we can actually have this answer sooner. I think so. For the unlimited money, that's what I would do. I would try to build the best telescope possible, because sometimes it's depressing when you look at national budgets. And I think in Jim Cassing's book once, there's this footnote, And he says the entire budget for a TPF, like this telescope that could do like hundreds of these planets, is 2 weeks of air conditioning during the Iraq War is what we spent, so it's sad, so I mean, these, like, they're expensive, but they're not expensive, if you know what I mean. So I think that it would be great to get these telescopes actually funded and launched through government, through private sector, however it works, and that would be if I had unlimited time, unlimited money. If I had unlimited time, I guess if I had unlimited time, I would probably also do more of my hobbies. I would do more mountaineering, some more dancing, do some more writing, and I'd probably do the same science, because I think that's what makes me happy, is having kind of a full life with lots of different things going on in it.
And it shows. So, assuming you have your $12 billion mission, it's flying. The next question from Jacob Hagmisra on Twitter asks, can you think of any spectral biosignatures that would uniquely indicate the presence of complex life on an exoplanet?
Yeah, interesting. So there is, this is not really a good area of my area of expertise. There are some technobiosignatures that's even a little more further afield, like signs of intelligent or civilization life. Some people have put forward like fluorocarbons, and signs like that. Dyson's.
But even like plants or fungi or animals.
Right, yeah. So for those, I don't really see, I mean, on Earth, it's like mostly microbes. You can't distinguish, like if you were to just look at Earth, you wouldn't necessarily be able to tell that there's human life here versus there's microbial life. Can't think of anything that's definitively, between technological signatures and just microbial life that would be a unique biosignature, other than I do think there's some energetic arguments to be made that you have to have oxygen. So you just get so much more energy from oxygen respiration than any other redox gradient that that seems to be a necessary precondition for multicellular life. And so that doesn't answer the question, because you would have oxygen without multicellular life as well, because that comes from oxygenic photosynthesis and from microbes. So but I can't think of anything between kind of the going straight to like technobiosignatures that would indicate multicellular life.
That's an interesting conclusion. The next question is from Bruno Pavletic on SciNet, and he asks, is there an online database with exoplanets and their atmospheres and spectra?
So, for example, on my website, I have all the spectra that I produced from my models. So I have grids of different types of Earth-like planets around different stars and different time points in Earth's history. You can go download them, play around with them, plot them on your computer. There's links to it on my professional website, so that's easy to find. And then as far as other planets, there's a lot of the exoplanets.eu and exoplanets, like some of those main exoplanet websites have a lot of the parameters just for various known exoplanets, not necessarily their atmospheres, but mass, radius, density, kind of other things that you can start to play around with as well.
Cool. Next question is from Jim Pass on Twitter, and I think it follows well what we've been discussing. In what ways can discoveries of biosignatures lead to those of technosignatures?
Right. So again, I'm not really an expert in technosignatures, though I did download the PDF on my computer to read that just came out about technosignatures. I think just being able to discriminate. So they're going to be the same sorts of fundamental technological hurdles to do either, and we're going to need high quality line spectra to do either. So one aspect that we haven't talked about that I think is really important is some of the high-resolution spectroscopy techniques and being able to detect biosignatures from the ground. So earlier and up to this point in the conversation, we've only focused on space missions. But you can actually detect atmospheres from the surface of Earth with big ground-based telescopes that are maybe 40 meters, kind of like the ELT, the Extremely Large Telescope that's by the Europeans. So that telescope with a high-resolution spectrometer can actually see the Doppler shift of the planet as it's going around its star. So the lines, and it can tease out Earth's atmosphere. So Earth's atmosphere, effectively, we're just looking through our column of atmosphere, and then it's looking at that exoplanet, and that exoplanet's moving compared to us. And so you can see, even if you are looking through all of our atmosphere, you can still see oxygen in that exoplanet atmosphere, because you see those oxygen lines going back and forth like a Doppler shift, like a siren engine, and it's pitch changing. You see the same thing with these lines. And I think that's really exciting. So by taking high resolution from the ground, we can get through our own atmosphere and see the Doppler shift of atmospheric lines around exoplanets for even Earth-sized temperate exoplanets. And not only that, the thing that blew my mind the most in the last year was you can detect isotopes in the atmosphere of an exoplanet. And that just, never did I think that would be possible. So you can detect things like HDO instead of H2O, or C13O instead of CO in an exoplanet. And there's some great papers by Paul Mollier and Ignace Snellen, which I'd recommend if people are interested in that. And so for technosignatures, often these molecules, they're probably not going to be huge imprints in the atmosphere. If you look at Earth's own atmosphere, us as humans, we're influencing, of course, the atmosphere with CO2. However, CO2 is also produced naturally, so that wouldn't be a unique sign of technology, right? So you're looking for these more niche molecules. You'll need a lot of good resolution spectra, and I think maybe high resolution spectroscopy from the ground is going to be the way to detect those. That would be my guess.
So it's essentially an engineering problem at this point.
Yeah. And also kind of imagining, we thought with SETI that radio waves are the big deal, right? Because, we produce radio waves in abundance. They travel very far. But now most of our communications are going in fiber optic cables under the ocean. We're not even producing a lot of those anymore. So I think it's hard to predict what a technological civilization will be producing, would be the other thing. But if we have enough high resolution spectra of these different molecules, and we see something really bizarre, that's just that's not a molecule you get in anything, from chemistry, then that could be an interesting follow-up.
Right. Maybe a civilization is only, emitting for a short period of their lifetime.
I know,
the radio wave.
Or they're then doing entirely different things that we're really, we're kind of necessarily hamstrung by our own experience, and so we first have to look for things that we can recognize before we get warp drive and a Starship Enterprise, and we can just jump around and see the whole, galaxy and start really exploring in that way. We're kind of limited to trying to tease out what we could detect, which is inherently going to be more similar to Earth in that it more carbon-based biochemistry, so to speak. Stuff like that.
I'm glad you brought up Enterprise, because this month we had a faithful little spaceship from Earth, dear little opportunity that after 14 years of hard work did not call home after being covered by dust. It was very sad. Perhaps you can talk about the importance of such missions to inspire the scientific community, to trigger new questions, as we take 30 seconds to remember little Oppie.
Yes, I know. I'm really sad. Had a good run. Better run than anyone could have thought. I think the mission lifetime was 90 days. It's 14 years later. I love the cartoons that people made about it. But I think especially for astrobiology, there's so many different avenues that are interesting, which is why you should all go into astrobiology, because you can go from any direction, from prebiotic chemistry, biology, whatnot, and it's all fascinating. And when I think about it from a planetary perspective, there's exoplanets, which is cool, but then there's solar system planets, which are also awesome, and those are the ones that we can actually go and visit and, actually find out, does Mars have life on it today, or did it have it in the past? The only way we're going to know is by going there, because Mars is not a global atmospheric biosignature case, right? We would have known that by now already. So the only way to find that out is to go there, to drill, to figure out what's happening on the planet. And I really hope we do that. My personal pitch to Elon Musk, should he be listening, is please don't send humans before we've answered this question and before we've irrevocably contaminated the planet. I know that we need to be multiplanetary at some point, but we have one chance not to screw up Mars. Let's not screw it up, please. Okay.
Yeah, I think we're further ahead in the engineering of space exploration than we are in the sociology and ethics of space exploration.
I know, and if I have 10 minutes with Elon, that is going to be my pitch. Should I ever get that opportunity? But yeah, so I do think going to these solar system science is amazing, not for just detecting is there life. Then you can maybe answer, is it a secondary origin or was it transported from Earth? That's also interesting. I think secondary origin to me is the most exciting, but also planetary transfer is super exciting too. And then say you find life in Titan, on like the liquid methane lakes of Titan. That's like an entirely different biochemistry than Earth. So the only way that we're ever going to be able to understand different biochemistries from Earth for an exoplanet is to kind of get a handle of them on a place that we can understand more, either in the lab through synthetic biology or like in Titan to see them in real life if they exist. So I think solar system exploration is immensely important for figuring out kind of more of the unknown unknowns that we don't even know, from our limited viewpoint on Earth. The only way to start addressing those is in part by going to the solar system and looking at places like Enceladus, Europa, Titan, Mars, and I think all of that is equally also exciting, So, yeah, I don't know. Science.
Solar system is full of opportunities.
Yeah.
Pardon the pun. The next question is from Mr. David Time Tunnel on Twitter.
Okay.
And he asks, do you think we might be able to capture an asteroid to put into orbit around Earth as a new moon? Is that possible? Is that likely? Is that just plain silly? What do you think?
Well, so asteroid capture. I mean, I think at some point we're going to be able to move asteroids and go to visit asteroids as humans, and maybe even do asteroid mining. And one of the main reasons for that is because they're undifferentiated, so more of the rare earth metals that have sunk to our core are still in much higher abundances on asteroids. So that's like the economic reason. I think we'll have the technology to do that. I don't think, we want to create we're not going to move another moon-sized object. I mean, the moon is huge for our Earth for stuff. But I do think we can probably nudge some asteroids. And also I think it's kind of important, going back to at some point it would be good to be multiplanetary, just hopefully not before we've adequately scientifically probed Mars. A huge asteroid impact is still an existential threat that we don't really have the technology yet to avert that crisis should it happen. We would have to know about that asteroid really, really far in advance and be able to nudge it from a very far orbit in order to prevent it from hitting Earth. Kind of the Armageddon sort of movie scenario is unlikely. So I think that this is something that we should devote some resources into doing, just to help our own, avoid catastrophe and extinction. The chance of that is low, but I think we should spend some time on that. And in doing so, I'm sure we'll be manipulating these asteroids.
Thanks, Sam. I think it's a promising future for humanity to take advantage of the resources that are in our solar system. Absolutely.
Speaking of big plug, can I just say big plug to the Expanse series? If you have not watched the Expanse series, and anyone watching this, so good. It just gets better and better. Give it the first 4 or 5 episodes because they're kind of slow, and then it just takes off. All right, okay.
Good plug. Next question is by Richard Gordon on SegaNet. And he asked more about the scientific process of getting data back from telescopes. How is it decided who gets to analyze the data, the spectra that comes back from those space telescopes?
So typically what happens is we put in telescope observing proposals for these space telescopes' time. Something like Hubble, if you look at the cost of the mission, right, and then average that over its time and the mission lifetime, it's about $1 a second. So it's very, very pricey. So you have to competitively petition for that time, So you're not paying that. That was already funded in the launch of it and whatnot. But the point is that they're very competitive, these missions. So only roughly 10% of telescope proposals are accepted. You propose to look at a certain target, you give a good science case, you tell exactly how long we need to observe it to get the science out that we want. And then if your proposal is accepted, you get proprietary access to that data for a period of time before it becomes public data. And so you can then write your paper on it or use that and study it. So I am a theorist, so I don't do this myself, but I am a co-I on several successful Hubble proposals. And that's essentially what happens is you have a period of time where you have that data and you can analyze it and then you publish it. And then it gets released. At some point, it's all archived. So you can go on NASA's website and look at, the IUE, which is a satellite that I use a lot. That's all archived data. You can go, you can download it, you can plot it, you can have fun with it.
Cool. Thank you for that. So we're really close at our hour mark, Sarah. It's been an absolute joy. Perhaps I'd like to close this beautiful interview with perhaps you have some final thoughts on perhaps to our younger audience on how to get involved in astrobiology in the first place.
Right. So don't do what I did, which is not take a breadth of science courses. I didn't take a single astronomy course, for example, and I didn't take a lot of chemistry. And I think that if I could go back in time, I would take more of everything. I would take more geology, more chemistry, more biology, and just realize that science it doesn't have these barriers that we put in it between these disciplines. Like most of the interesting science is happening at the intersections of these borders, and biochemistry and astrobiology is being the quintessential, I think, example of combining all of the sciences together. So I think as a young scientist starting out wanting to do astrobiology, while I'm sure there's a certain area that interests you and pursue that area, try not to do what I did, which is say, but squiggly lines are boring, and ignore everything to do with astronomy as a result, and then feel completely out of place when you decide that's what you want to do. So take just a breadth of science courses. I really do like Genesis, the Scientific Quest for Life's Origins by Bob Hazen. He also has some other books like Story of Earth, and just read about a lot of the cool astrobiology sort of broad survey books that have come out, and go into it. It's so exciting. I just have never looked back. It's been an amazing time.
Fantastic. I think it's a wonderful place to close this interview, Sarah. From a personal perspective, it was just an incredible adventure having this conversation with you. We went through so many topics. Everything was fascinating. I hope those of you who are watching had a similar good experience. Don't forget to tune in next month for Ask an Astrobiologist. Don't forget to guess what is the picture behind me. Until then, everybody, stay curious. Bye-bye.